Okay, so today it's my pleasure to introduce Dr. Bingbing Ni, who is a postdoc researcher at ADSC in Singapore, and is visiting Illinois this week. He actually got his PhD from Shanghai Jiaotong University, right, in 2005. No, sorry, your bachelor's degree in 2005, and then he did his PhD at NUS in Singapore, National University of Singapore, and you received your PhD in November 2010, right?
Yeah.
And then around that time, he started working for ADSC. He's interested in various aspects of computer vision and multimedia computing, especially actually Kinect camera and the multimodal processing. So he's going to talk about some of that work here today. And then he has another talk on Friday at 3 p.m., which will be announced soon again on another topic in computer vision. But right now, I will leave the floor to Bingbing. Thank you.
Thank you, Pierre, for introduction, and thanks, Katie, for arranging all the meetings and the seminars. So I'm Bingbing Ni. I'm a researcher at Advanced Digital Science Center, Singapore. So I'm working closely with Professor Pierre Molin in UIUC. And oops. Oh, works. Okay, this is a very famous slide created by Marianne, who is the director of ADSC. So this shows the things we are doing at ADSC. We actually under the sub-program of interactive digital media. So we have lots of things in the IDM program. We do visual, we do audio, and we also do data mining and networking. So actually, Pierre and me are working on the computer vision domain. More specifically, we are working on using the Kinect cameras, which is a very cheap depth camera for recognizing actions, recognizing activities, and also we do human motion tracking. So I think most of you guys already know Kinect is very popular these days. So the introduction of Kinect creates many opportunities for the computer vision research, because it has lots of advantages. For example, it's the first device which can directly sense the 3D scene structure in a low cost. And if someone can sense the 3D structure, so it's easy for the foreground and background segmentation. And also you can access the 3D motion of the scene. Because if you just take the depth videos, you cannot distinguish who is inside. So it's pretty much good in the privacy preserving. And of course, it's a very low cost device, typically for indoor use. So today, this is the outline of today's talk. So first, I will give introduction to some very interesting recent Kinect-based applications. I think maybe some of you already seen these applications online, but here I will give a short introduction and summarization of them. So after that, I will present our recent works and some preliminary results on the Kinect-based project. So we actually do Kinect-based tele-rehabilitation, and we do action recognition and also the event detection. And after that, I will conclude the work and give some future works. So here's just a list of some example applications of the Kinect. Actually, the Kinect has various of applications. Here I actually divide them into two groups. So the first group is the low-level image processing-based application, and the second group is high-level visual semantic-based application. So in the first group, we can have lots of applications such as 3D reconstruction, image enhancement, video stabilization, and video segmentation. And for high-level vision application, I think most of you guys are familiar is the game, which tracks the body poses and interact with the computer. And also we can have foreground and human detection. And we can also have gait analysis based on Kinect. And there's also some interest work on using the Kinect for indoor spatial layout modeling. And yeah, lots of interaction-based applications. So this is the most straightforward application, which is 3D modeling, as Kinect can sense 3D as a depth value, so it's quite straightforward using that device for modeling the 3D scenes. So Microsoft has this project called Kinect Fusion, which creates real-time 3D modeling of entire indoor room. Very recent, I think this work is just accepted by CVPR this year. So this is a work which using the Kinect camera for video stabilization. So previously, people using the color images for video stabilization, which they do is they calculate the homography between nearby frames, and they calculate the camera movement, then do the registration and adjustment of the images to stabilize the videos. But as we all know, because if the scene has many depth layouts, so that method will fail. So if we have the depth information, so it will be more easier to calculate the camera movements, so that can register the images better. So also, as the Kinect gives 3D the depth value, so it's quite straightforward to using that cues for image segmentation. So if we combine the color and the depth together, so the segmentation results could be better. And here is application on human detection, which is also known as foreground detection. You can see from the right image, because some person's color is confused with the background, so they might not be very easily detected. But using the Kinect-based device, so human can be easily detected because their depth is quite different from the background depth. And also, the detection could be in the 3D domain, means that once the detection is not a 2D bounding box, but is a 3D volume in the 3D space, which is pretty nice in the surveillance applications. So I think most of you know this application. Yeah, it's Microsoft Kinect for game application. So this work is based on the very famous paper by Jamie Shorten from Microsoft Research, which is using the single depth image to infer humans, the 3D joints of the human. And after we get the 3D joints and the poses of human, and there are lots of quite interesting and very useful applications. I think PI likes this application pretty much. It's application in the surgery room. So before this, the surgery there will be quite troublesome for the doctors. They during a surgery time, because they need to wash their hands from time to time to just browse the PCs for some documentary, for some images, or for some localization of the cancer or tumor. But now with Kinect, they can avoid this kind of trouble, and so that it's more safe for both the doctors and the patient.
So how does it work? Motion gesturing?
Yeah, so actually for the browsing, they can wave the hands to browsing the images or documentary, or they can using the two hand to control the images of maybe the brain, or under some CT or X-ray. So that's to avoid the contaminations. Yeah, it's a very, very nice application actually. So also because for this interaction-based applications, we have online shopping to browse different products. So and also the control of the PCs and browsing the internet, browsing the multimedia content. Yeah, so it's all based on the inferred pulse of the humans. And we can also have this gait analysis application because Kinect, using the Kinect data, it is much easier for people to do the foreground and background segmentation. So you can easily compute the silhouette of the human. So that creates the opportunity to do more robust gait analysis. And of course, there's a very, I think lots of people now focusing on the rehabilitation, including our group, using the Kinect, because Kinect can track the human's poses, and they can interact with the virtual world in the computer, so that the therapists can encode their exercise in some computer games, and the patient can interact with the object or subject in the system, and so do the rehabilitation. And here is another example. So Dr. Ji-Wen Lu and Dr. Gang Wang in ADSC also did this work, which is using the Kinect for reasoning the spatial layout of a room. And of course, some interactive applications for the arts. It's like painting in the air or draw something. So now I'm going to talk about our recent works in ADSC using based on the Kinect. So actually, our goal in ADSC is to effectively and robustly doing human action and event analysis using the consumer depth cameras, which is Kinect. And because this one is actually is a very challenging work, it's a very challenging task, because you can see that lots of very complex background, and also the changing of the viewpoint, changing of the appearance of the humans, the scales of the humans, and also the occlusions and illuminations. And using the Kinect camera can help to improve the performance. So here is the roadmap of the project. So we do 3D human motion analysis, we do human action and event analysis, and we also do human activity analysis using the Kinect camera. And the target application of us is so first is a smart office demo in ADSC. So this demo is an integrated demo which tracks the people, identify the people, and identify what the people are doing in the office, such as pouring some water, make some coffee, and discussion, and working. And also one of our key application is rehabilitation using the Kinect. And also we are interested in apply this technique for monitoring the daily activities for the elderly. So this is a prototype system we created in ADSC called Kinect-Based tele rehabilitation. So actually, based on the Kinect SDK, we developed such an application. The purpose is to implement the Fuga Maya. This is the name of some doctors which suggest the exercise, the Fuga Maya upper body exercise protocol. So what the system do is they track the movements of the human, and it infers the key parameters of the joint angles, and also the number of movements, and it tells doctors, and also it has it also has a function of for automatic alarm if the human is doing it wrongly. For example, some wrong pose. So this kind of system will reduce both the cost of the physical therapist and the patient in terms of the transportation, in terms of the medical consultation. And we actually have a demo video online. Probably I will show it in the Q&A session because it's pretty long. So actually in this system we have implemented about 12 kind of exercises, and some of the exercises the doctors are interested in the range of movement, and in some of the exercise the doctor are interested in the different number of movements. So yeah, I will show you the video later. So the second work we do in ADSC is using the Kinect for action and activity recognition. So our target application here is recognize human daily activities for the elderly. So to do this task, first we create a Kinect-based video database which contains these kind of activities. So the setup of the video capturing is we're using the single Kinect camera, and we record both RGB and depth image sequences. The resolution is 640 by 480 pixels, and it works on 30 frames per second. And we're using the OpenNI platform for do all the capturing and processing. And the data is collected in our ADSC office, and we actually invite 30 students to participate in the video taking, and they are asked to perform the daily activities. So in total we actually have defined 12 types of activities, plus one neutral, which is a background activity. So the 12 activities, they include make a phone call, mop the floor, enter the room, exit the room, go to the bed, get up, eat meal, drink water, and so on. So they are typically typical daily activities we are interested. So below is a summarization of the video data we have captured. So we have 30 subjects, and we're capturing their activities under 14 video capture sessions. And so about 48 hours of videos we captured with us, and they are manually segmented into different activities. And totally we have about 1,000 video samples, and each sample spans about 30 to 150 seconds. I will show some examples in the next slides. You can see there are large intra-class variations, which makes the task challenging. And actually this database is public available. You can download from our ADSC page. So here is sample frames of this data set. So you can see actually there contains lots of intra-class variations. For example, the activity drink water. So some subject will drink water in a standing pose, and some subject will drink water in a sit-down pose. Of course, for the activity put on the jacket, so different people has different ways of doing such action. So these kind of variations makes our problem more challenging. Okay.
So I also noticed that the inter-class are very similar actually.
Is it?
Right. So between two classes, like making a phone call
The interclass are very
interclass are very similar.
Similar,
And they cause
okay.
like even more problems.
Yeah, you are right. Actually, I think for some classes like put on the jacket and take off the jacket is visually is quite similar. So I think
why is it similar? In one case, when the jacket is separated from the body, it's either the beginning or the end of the sequence.
So I think it based on which kind of features you use to distinguish them. Nowadays, nowadays there is a type of task called fine-grained video classification. Action classification means that the difference between classes is pretty fine-grained. It's like only the hand movement is different, but the whole body should be the same. So I think it depends on the feature use. If you're using some very coarse global features, you might not be able to distinguish these two motions. But let's say you have some well-designed features for the movement of just the hands. Maybe I think in this case you can distinguish these two classes. So this is actually what we are studying now. So after we create this database, we also propose two features, two action-based features from the depth sequence to do the action recognition. So the first feature we developed is so-called the 3D motion history image. So motion history image is a very famous motion features for action recognition in a color sequence. The motion history image actually measures the motion recency in the recency of the motion for every pixel. So in our case, we extended to the depth channel, which is we encode the movement recency in the depth direction. So we actually divide the depth-induced motion into a forward motion channel and backward motion channel to distinguish forward movement and backward movement. So here is some examples of the motion history image and the depth-induced motion history image, and so including the forward motion and backward motion. And in our experiment, we evaluate the performance for motion history images, depth-induced motion history images, and also the combined three-dimensional motion history images. And the parameter, the duration parameter is set empirically. And this types of feature representation is very simple and efficient, which can be very easily extended to multiple view representations. And so after calculating these motion history images and 3D motion history images, we're using the hue moments to calculate the statistic of this image and to serve as features for our classifier training. Now here is some experiments. So we're actually using the Liu 1 subject out classification scheme. The reason to use this classification scheme is that to make the experiment more challenging, because if you using the same person as training or testing, that will reduce the difficulty of the problem. So we actually using 29 for each time of running. We're using 29 subjects as training videos, and another one is taken as testing videos, and we rotate every human and to calculate the average performance. So we're using the both linear SVM classifiers and the nonlinear RBF kernel-based SVM classifiers, and the performance is shown in this table. You can see that Actually, the results is very interesting. You can see the depth-induced motion history image performs much better than the color image-induced motion history images. And we thought the reason is that in our dataset is lots of forward and backward motions, and these are quite discriminative for distinguish different actions. So that's the reason why the depth-induced motion history image is doing pretty well in this case. And once we combine both channels, the performance could be further boosted. And also, the figure shows the confusion matrix for different activities. And the second feature we designed is so-called depth layered multi-channel spatial temporal interest points. So spatial temporal interest points is nowadays has been a standard features for action recognition and video event analysis. So our basic idea is to divide the 3D space according to the depth channel, according to the depth value into different layers, and we do the feature pooling within each layer, so that the resulting features is a multi-channel histogram representation for the spatial temporal interest points. So here is the whole pipeline of processing. So first we extract the spatial temporal feature points from the color image sequences, and we do the vector quantization, and then we divide the depths into different channels, and we do the feature pooling within each channel. Then the result feature representation is actually the multi-channel representation. So here is a diagram shows this feature extraction. So we extract the features from the color images, and we do the we do the vector quantization using this trained visual vocabulary, and then we do the feature pooling. We do the feature pooling within different depth layers, and then the resulting is a multi-channel backwards representation. Here is some experiment results. So we're also using the leave one subject out scheme, and since it is histogram-based features, we're using the chi-square distance to train the SVM classifier, and we also try different codebook sizes. We also try different number of depth layers. And we compare this our performance with standard STIP-based methods, and as you can see in the table, so using the multi-channel STIP representation will give improved results over the traditional STIP-based method. The third project we have been working on is a Kinect-based event detection. So actually, so we have collaborations with the National University Hospital in Singapore. So they actually want to do the fall prevention, because the fall is the highest risk in the hospital ward. So we collaborate with them, and we thought that perhaps we can do some event detection to prevent, like if we know the people who are going to get up from the bed, then we can alarm the nurses come for assistance, so that to minimize the risk of the patient falling. So we then using the Kinect device to doing this project, and we using the color and depth fusion based method to do the event detection. So here is the pipeline or diagram for the whole system. So our capturing device is a Kinect, and we capturing both the depth images and depth sequences and the color sequences. and we detect the event. We detect the event when the patient is trying to get off the bed, and in this work we apply the multiple kernel-based method to fuse both color-based features and depth-based features. And once we detect event, we will alarm the nurses for coming to assistance. Here is a feature extraction of our methods. So we think that for this kind of problem, we can using the domain knowledge to design an efficient and effective set of features. So in this case, we can actually we can define some region of interest surrounding the ward bed area, because the get-off event will usually happen at that area. So we divide the area into 8 blocks for both the depth channel and the color channel, and we also extract different types of features from each of these blocks. The features we used include the histogram of oriented gradients (HOG) and histogram of optical flows (HOF), and motion history images. And we fuse these. We fuse the different types of features and different geometric channels in multiple kernel fusion framework. So here is our multiple kernel fusion framework. So we actually fuse the features from different channels and features from different types of features within this multiple kernel learning framework, and we're using the simple MKL solver to solve the optimization problem. This is the experiment setting. So we actually collect 240 video samples, which including 40 positive samples from 4 subjects in the hospital ward, and the testing scheme is also the lean 1 subject out. And we compare the detection accuracy, the receive operating curve using different feature channels and their combination. And we also compare with the state-of-art event detection method, such as the AIP-based method and the recently proposed dance trajectory-based method. So here is learned kernel weights from different channels, and different feature types. And you can see the solution is quite sparse, and you can see the channel tree mostly receives the high weights. So if we go back. Sorry. So if we go back, you will find the channel tree is at this area. So actually, the gate up motion is mostly happening in that area. That's why this channel receives a high weight. So actually, in this version, we define it manually, empirically. But actually, we can have more regions, and we can using the learner to learn the best regions. So it doesn't really matter. So here is the weighting, and here is the ROC curves for the different features and the combined features, and we can see that using the combined features, the performance is the best. And here is some recognition, the recognition accuracy using different features and the combined features. You can see that in this case, the M motion history image using depth channel only gives the highest performance. But we think that in general, the multiple feature fusion will give the highest performance. And we also compare the our detector with the state-of-art event detector, such as spatial temporal interest point based detector, and also the dense trajectory based detector. These are two detectors are only based on the color channels. So you can see that combined color and depth will give the highest performance. So conclusions. So first we develop a Kinect-based upper body rehabilitation prototype system in ADSC, and we create a RGB depth database on daily activity recognition with over 1,000 video samples with 13 categories. And 2 types of depth image-based features are introduced for activity recognition. And we also develop RGB and depth combined based event detection for hospital for prevention. So in future work, so first we will develop a better user interface for our rehabilitation system, and we will include more scene variations and real video recordings for the database. Since the current database is still quite simple, and they do not have the real video recordings. And we also will develop new depth-based features and develop new feature fusion schemes and machine learning schemes for better classification and detection. And for high-level human activities, and actually what we are doing, we will develop human object and human environment context models for complex activity recognition and localization. So this is my presentation. So actually we have a video for the rehab. So I think when you are asking questions, I can play that video. Because it's on YouTube, I cannot download it.
But you can, right?
I cannot download it. I don't know.
Flash. Yeah. Just store it as Flash now.
Oh really?
Yeah.
Oh, so I cannot online here. We don't have the internet. Oh. I don't have the account. You want to come?
Hey, Bingbing, I have a question. For the GitHub event detection, is that done in real time right now?
It's not exact real time. It's very near real time right now. Yeah. So, but the current implementation is all on MATLAB platform. So I think we have the potential.
When you say almost real time,
it's like
more specific.
it's like 1 frame per second.
1 frame per second.
Yeah, processing.
So it could still be real time, just low temporal resolution. But is it real time or is it low temporal resolution?
You mean to reduce the sampling in temporal?
Well, to make the decision, is the person falling? Is the decision made real time or no?
It should be making real time.
Death before you recognize that he has fallen.
It should be in real time actually.
It should be, but is it?
It's not at this moment. We treat it as a binary classification.
Okay.
Thank you. The music is very exciting. It's Marian edited.
Patients who have suffered a stroke or other brain damage often need physical therapy to be able to carry out activities of daily life, such as walking or feeding themselves. Physical therapy can also be important during recovery from sports mishaps, car accidents, or any other kind of injury that has impaired normal functioning or limited mobility. The Advanced Digital Sciences Center has developed a camera-based automated assistant to help patients perform rehabilitative physical therapy at home as an application of ADSC's basic research on recognizing actions and activities in video. Professor Pierre Moulin from the University of Illinois explains the project to ADSC Director Marianne Winslet.
Having been to physical rehab myself, I know that traditionally you go to the clinic and the physical therapist watches you do the exercises. And what's wrong with that traditional approach?
So one of them is the direct expense for the patient. Instead of having to go to the hospital, they can stay home. And then maybe the biggest saving is in terms of time of the physicians and the physical therapist, because the system is now automatized, and basically you have a system at home that does this monitoring as opposed to taking time of physicians and physical therapists.
I can see that if you're old and you had a stroke and you can't afford a taxi, then getting on the bus to travel across the island would be exhausting and impractical. But then on the physical therapist side, how does it help them to have a video of the patient? Don't they still have to watch the video?
Not necessarily. In fact, they really care about the data. Okay, so all these angles and all these motions, which are extracted by the system and reported as part of the summary, is what matters to the physician. So they don't need to spend, say, half an hour watching the video.
Oh, okay. So it's more convenient for the patients, and the physical therapist can handle more patients without getting stressed, so it would be lower cost to society as well.
That's correct.
In this demonstration of the physical therapy assistant, ADSC's postdoctoral fellow Bingbing Ni and software engineer Pei Young have placed a depth camera at chest height. This is a Kinect camera from Microsoft's Xbox, which costs about $150 in the US. Pei has put the camera on a small tripod on his desk. At home, the camera could sit on any piece of furniture that gives an unobstructed view of the patient's body. Pei's camera is connected to an ordinary PC, whose monitor is next to the camera. Bingbing stands in front of the camera and watches himself on the screen as he does the exercises. The assistant has been trained in advance on a repertoire of exercises, in this case, shoulder exercises. The assistant's current interface allows the patient or a family member to select between the exercises assigned to the patient. Once a particular exercise is selected, the screen shows a reminder of how to perform that exercise. As Bingbing performs the exercises, the assistant watches him, evaluates his performance, and counts his repetitions. If Bingbing isn't doing an exercise quite right, the assistant notices this. For example, here Bingbing is swinging his arm from side to side instead of in a circle. The assistant does not count these repetitions. Or, if Bingbing's posture is wrong for a particular exercise, the assistant asks him to change his position. Traditionally, all these functions would be performed by a physical therapist in person, rather like a personal trainer. The therapist selects the exercise, counts the repetitions, and evaluates how well the patient is performing. If there are problems, the therapist helps the patient understand what he or she is doing wrong. To monitor a patient's performance and progress, the therapist may use objective measurements, such as whether the patient can raise his arms straight over his head. ADSC's automated assistant can also capture these measurements. For example, here the assistant shows how close Bingbing is to the goal of lifting his arms straight over his head, 180 degrees from where they started at his sides. Here the assistant counts repetitions of Bingbing rotating his arm. Here the assistant shows how far Bingbing has lifted each arm. The goal is to reach a 180-degree angle. And here the assistant shows how far Bingbing has bent his elbow. Bingbing could be holding hand weights while he does this exercise. The assistant will send a summary of the completed exercise session to the physical therapist so that the therapist knows how the patient is progressing. Video clips from troublesome parts of the session could also be sent to the therapist. If needed, the patient and therapist could use the internet's free video chat facilities during a session to allow each of them to see each other without a trip to the clinic, which can be very difficult for patients with limited mobility. But sometimes there's no substitute for hands-on interaction. In that situation, family members often take time off work to help the patient travel to the clinic. ADSC's assistant can reduce the frequency of these trips. To add a new exercise to the assistant's current repertoire, ADSC films examples of people doing the exercise correctly and incorrectly, and runs machine learning algorithms that analyze the footage and determine the characteristics of a correctly or incorrectly performed exercise. ADSC is working with 4 Singapore hospitals to try out the assistant in clinical and home settings: Singapore General Hospital, Changi General Hospital, Ang Mo Kio Tai Hoa Kwan Hospital, and the National University Health System.
Thank you. Thank you.
Thank you very much. I think it's time for more questions.
For the first feature, could you put like the linear SLAM and the SLAM? However, for the linear SLAM, the technology is better.
Yeah.
Why?
This one. So you suspect every time the nonlinear SVM is gives a higher performance, but I don't think it's true in general. So it depends on the features you use, because for I think for the histogram-based features, like is a global-based features. I think in this case, nonlinear-based kernels will be work better. But my case is actually not such type of feature. It's based on the images. So it's some local information. So in this case, if you using the linear kernels, I mean some information will be lost in nonlinear kernels. So that's why I think in this case, using the linear kernels may work better.
You did multiple kernel too.
No, for this work we don't using the multiple kernels. Yeah. But you can also give the learner to try to decide which is the best. But that's a black box. We will never know. I mean, it's a black box. I think better to know the characteristic.
So,
yeah.
For the motion history features, will you do some denoising on the depth images? Because depth images do denoising.
Actually, in this case, we do not do the denoising.
So, in your opinion, will denoising help?
I think will help, but I think it will help, but not significantly. Because this feature is like an accumulating feature, so it will be robust to some noises.
But I noticed that, like for the noisy depth images, especially on the boundary, there are many missing values. So
yeah, some missing values.
Not moving at all. Two consecutive images.
Oh, okay.
Yeah.
Okay, because after we get the motion history image, we will calculate the moments of the images. So in the moments is actually a globalization of the features. So some local variations might not be reflected at this.
But how about if they're missing values, as he says? So wouldn't that affect the global moments too?
I think it will affect, but not significantly. Yeah.
Any other question? Okay, well, thanks again.
Thank you. Thank you.
Yes, and so as a reminder, there's another talk on Friday,
Yeah.
3 p.m. I think. Right?
So Fridays?
3:01. Yeah, no, not 3:01.
Yeah. Oh, 3:01.
Okay.
So Friday's talk is about two regularizations.